Hello everyone watching. Likely just be myself. Caveman in this. Something interesting on the bottom of this. Some turquoise aquamarine color. I think it's likely like some nickel oxide maybe. Usually that's indicative of like copper oxides. It's kind of weird. Man, let's see if we can get in here and move this. I wonder if, I think I named the stream the same as the last one. Oh well. Whoops. It's basically gonna be the same. It's gonna have the same number. Clean this up a little bit. Yeah, that's interesting. I've never seen a turquoise deposits. I should probably collect that. Maybe it's from the aluminum tube. Oh, must have been. Oh shit. Flake of quartz there too. Ooh, that's gonna be hard to collect. It's heavy pieces. Still no. Couple pieces. Okay. Need a longer pipette. Yeah, that is not going to work. Well, shoot. Let's see. I got most of it. That worked. There we go. Yeah, that's interesting. Super interesting stuff. Alright, I think I cleaned up this cloud chamber a little bit. It's not as smudgy, but it's hard with the felt. The felt kind of leaves little pieces. And I got rid of I refelted it. I got rid of the sticky back. Still have to pipe up this. These are some chunky pieces. I don't even know if I can do it. A little bit. Just gonna use my finger. Yeah, that's super interesting. This will be interesting to look at. You can see it. See the blue in it? That's interesting. So usually I get grays from the nickel oxide, like the nickel hydroxide. It's not usually an oxide. This is like a blue. I bet it's from the ceramic because it's alumina, right? So it's probably from the aluminum. That's probably what it is. Interesting. That's got it from the ceramic melting and breaking. All right. So it's gonna go to the wash list. I gotta mark this real quick. Maybe I'll put on some tunes or something. See what was yesterday's date, 24th. Call this one ceramic break. Melt. I'll just call it break. Can't be sure if it melted. Could have just broke. Alright, another one down. So I am getting tracks, it looks like, which is good. Yep, getting small tracks. So, I'll get to that in a second. Alright. Put this back together. Just another layer of this on it. Oh yeah, fun times. I wonder. Oh, Mr. Friedman put out a new podcast. Guy from ChatGPT. I wonder if I'd get a copyright strike if I listen to that. I'm doing this shit. Probably. Not like I'm monetizing any of this shit. I just don't want to like, lose the video information. Okay. So I'm maintaining the same wire. Just gonna keep running with it because I still have it there. It did burn through some of the ceramic, but I still have some ceramic in place. So I'm just gonna roll with it. Of course, it's like always, it's hard to tell and see. I do have a microscope. I need to do microscope work on all this shit. I can get. I could probably. I'd have to download the microscope software on this computer. I keep having a problem with this falling over too, which is annoying. Already tried wrapping it once. That didn't work out very well. I'll try it again. Yeah, Josh, I have a microscope that I can attach to a computer. It's up there. I haven't pulled it. It's up on a rack. I haven't pulled it out in forever, but I've been needing to because I got lots of samples to look over. I'm supposed to look over some for the high voltage experiment too. I'm not really sure what I'd be looking for, to be honest. Just small deviations, small holes and pits, deformation. I mean, it's cool, but it doesn't really confirm anything. This is not an ideal approach. Man, maybe if I had a little... I don't like this. Because this gets so hot, too. I don't like doing this. It's not the best approach. So let's think about this. I could have mixed up some cement. I have some ceramic cement, but that'd take forever to cure. I think I'll just try to gently place it in there. Hope I don't lose it. So, wish me luck. Oh, lost it. Can he regain it? You guys can watch me screw this up. No. Son of a... If I put the water in it first, I might hold it better, but it's such a pain in the ass. I could put another ceramic piece on the bottom. Restrict the flow. Last time I did that, it kind of restricted the flow. Give it another go. This way. Let's go. Yeah, but if I lose it, I'll dump it all out again, so I'm not gonna do that. This. Steady. Stay. Got it. All right.
Digital one, I made a mini mix.
Yeah, I have lots of electrode samples too, so. I'm gonna be streaming for a while tonight because family's gone and I got nothing better to do. Dry ice has made it really cold in here though, so I had to put a hoodie on. Let's get some of this carbon fiber on in here. There we go. Lid off. Of course.
I lost a little inner piece. Of course. I think I have some more of them. Lost a little O-ring. Dang it. Aha. Nope, it's not it. Well, shit.
Alright.
I have another one here somewhere.
Yes, no, maybe so.
I could have gone far.
Oh, the little things, little mistakes. Well, I want the oxygen to vent off. Oh, this one's gone too. I think what I'll do, I want to really plug this one up actually. To be honest, I'm going to switch this out. I can get this out easier. at air gas, place where you can get like argon and nitrogen and stuff like that. But some grocery stores sell it too. But I think it varies state to state. Some places they don't sell it. I'm not sure why. Some danger in it. Maybe trying to deter people from making drugs or something like that. I don't know. Drugs or bombs. Probably has to do with one of those two things. Oh shit, can I say those things on YouTube? Damn, I might get canceled. Better be careful with what I say, huh? Some algorithm is looking for those audio signatures, those keywords. So I'm gonna put a little PTFE tape on this O-ring because I really want to constrict the amount of hydrogen that's leaving this. I don't want the hydrogen to leave the system, just the oxygen. And then it's just gonna have just a poke from. There we go. But I'm stupid. Because I have to put the other thing on first. So why don't we put this on first? Here we go. Okay, let's re-rack this a little bit better. That's good. As long as I'm not constructing one, right? Although some people may think that's exactly what I'm doing. I'm not. You know what I realized is, no, the chat box should be popping up. Right? Chat box should be popping up. Yeah, there it is. All right. I don't know how good the stream is. Like, Saturday nights can kind of get bogged for some reason, I notice. So we'll see how it goes. But I'll be doing this for a while. And while the experiment's running, maybe I'll crack out the microscope and look at some past samples. So I'll probably just do another duration test. I'm going to do this cloud chamber test again too, but after yesterday I don't have high hopes that it's going to yield anything specifically. Nothing of great importance. Go. Okay. You can see the magnet there. I think it got too cold. Might have to warm up the. Yeah, I might have to warm up the felt. What's up? Yeah, I'm gonna do another plasma electrolysis experiment with the cloud chamber, see if we can see anything again. Give it another try. Might as well use up all this dry ice while I have it before it all evaporates or sublimates. I think that's what you call it. Yeah. Alcohol gets cold though, and then it doesn't create the vapors on the top. We gotta have the vapors. Also, get that ice buildup too, the humidity. I was going to try to run it on top of it, but I have to reconfigure everything and rewire everything differently. It'd be kind of a pain, so I'm just going to run it next to it again. Okay. White again. Okay. Let's see how we do. Still probably hard to see, huh? Mm-hmm. Okay. Attach. This. And attach. This. And attach. This. And attach. This. And warm up the top. I'm gonna go get a warm Tupperware real quick. Before I do that though, go like this. Do this. Yep. So we got that. This anymore. Start warming this up. Oh, helps to plug it in. Safety first. Okay, let's try this again. There we go. 9 volts hitting the cell. Kind of want something different here. Hold on a second. We're gonna go. This one's even called plasma. Let's see how this one does. There we go. We'll go with that. Okay. Be right back. thought about it, and I realized it's probably not going to transfer heat very well unless I use something made out of metal. So there we go, the little coffee thing. Hopefully that'll heat it up enough on the top. Yeah, I'm seeing tracks. We're looking good. Okay. What else we got here? You know, from the last thing we said too, I can try to get temperature readings of the water by opening up one side of the cell too. So I'll probably do that, and then I'll make some space here, pull out the microscope. Try to get this going a little bit, but I'm gonna go to the bathroom real fast, grab a drink, and then I'll be right back. Commence, and I'm also gonna throttle this up a little bit too. Yeah. Okay, let's turn this up a bit. Go to 24 or so. Alright, I'll be right back. All right. Take this off. Microscope. Okay. All right. Now I'm getting hot. And I'm gonna check the stream and see if how it looks, if I can get this. To be at about 60 C and 100 volts to get a plasma to ignite. I'm surprised how low voltage you are applying. Yeah, so it depends on your electrode and it depends on your current density. Turn this down a little bit. There we go. So it depends on your current density. So if you make a really small negative electrode, right? If you make a really small cathode surface area, but you put a lot of current density into that, so a higher voltage into that smaller area, it's more likely to make a plasma. Just the same reason why if you only put a little bit of the wire or the rod into the surface, the top surface tension, it increases the current density and you can get plasma ignited a lot easier. But you're right, when you increase the cell temperature up to 60 C, I don't know if it's because there's more resistivity in the cell that it does that it makes it easier to ignite the plasma, or if there's some talk in the scientific circles that water goes through another phase shift that makes it more coherent between 60 and 90 C before it reaches the steam state, before it starts to turn into steam. It becomes more coherent, so the water almost acts as like a semi-solid or a I don't want to say super fluid, but like it just moves like atomically. It moves like more like a solid would. So it's kind of interesting. It's like a non-Newtonian fluid. I don't know what you would call that, but there's some papers on it. I think I have it linked on the magnetohydrodynamic plasma paper on the website. So you're able to, and also if you increase, there's chemistry balance too. I use about 17 grams of KOH. Yes, 17 grams of KOH for 600 milliliters of water. That's my recipe that I use. It seems to work pretty well. So it's not too resistive and not too conductive. Where you're just you can't even get a plasma because it's just dumping so much Yeah, exactly. That's what I'm saying. Is there's a higher current density, so you can use a larger rod, but you have to cover it with, like, I use this like ceramic to cover it, or just put it just on the surface, just barely into the surface of the water. The challenge with that is you have to keep it level with the water, and if you boil off the water, right, then so you have to slowly adjust it down into it. There could be a way to automate that in the future. I think that'd be a pretty good engineered design. And there's a group of Russian scientists who did that. They took a bunch of, like, a whole network of cathodes and a very, very tiny wire, basically, and use that just on the surface tension of the water. And if you look at my, I don't know if I've ever, yeah, I showed it to you, the high voltage DC. I just do it right on the surface tension of the water in order to get that current density up, because it doesn't have a lot of current, it doesn't have a lot of amperage, right? It's just high voltage, and it only has like 15 milliamps. So you have to make a super saturated solution, and then you just put just the slightest amount into the very surface of the water, right at that interface, that boundary layer. There's something really powerful about that, where it just increases the current density to such a huge degree that, you know, you can actually make a plasma happen. It's pretty cool. So I'm gonna turn this up a little bit. Check the top of the glass. Yeah, and you can DM me too, and I'll send it to you. I could post it into the stream, actually. Just give me a second. You want the paper for the phase shift of water, right? That's the one you're curious about. I don't know about the Russian one. It was something I saw a long time ago. I haven't seen it since. And I didn't save it. It wasn't a paper. Actually, I might have it somewhere on my computer, but it wasn't a paper. It was an actual video I saw. So, oh, that might be why. I think because I tilted it, it wasn't, it had an air leak. Input. So we'll have to wait for a second for it to start working again. Yeah, there we go. Yeah, cool. Okay, so paper. I don't know about this music. Something a little more chill. Lo-fi stuff. Try this. This might put me to sleep though. I really like this one, but let's do this one. Try this one. Okay. Paper. Yeah, I'll find it. I'm looking at it right now. I'm looking for it right now. Oh, the missus is calling me. Hello.
Hi.
I'm streaming. Oh, looks like it
It's so beautiful.
cleared up. Yeah, it looks beautiful.
It's so nice. Yeah.
Nice.
And you want to know where we're at? Where you and I stayed? Remember these stairs?
Oh yeah, yeah.
And then we stayed up there.
Yeah. Looks beautiful,
I
babe.
remember we couldn't get a water, and that guy came out and gave us some water, and he was like watching with you.
Yeah.
And then we took our money
Yep.
in that hotel. So then
Yeah.
we're in a really nice one. We're on the bottom.
Looks beautiful.
Anyway, just wanted to share this view with you.
It's pretty.
I love you.
Love you too. Yeah, I'm streaming, so you can hit. I'll be streaming probably most of the night, so you can later when you go back to the hotel, you can go to YouTube and say hi there too.
Your cloud chamber.
Yeah, cloud chamber and the plasma reactor, and then I'm gonna do some microscope work. I have to download this, so.
All right.
All right.
I love you.
Love you too, babe.
Bye.
Bye. Hello, Googler. What's happening at the end of the nickel titanium cathode? It's a radical phase shift from liquid to gas to plasma. So you can actually get a plasma in a liquid. Okay, sounds good, Josh. I'll be here for a while. I'm gonna set up this microscope. So hopefully that helped answer that question. If there is some. Oh, that's right. Before I got called, Josh, here I actually got that paper. Did I close out on it though? Crap. I did. Okay, I'll get it real quick again. I'll put it in the chat. I looked for more papers on it too, but unfortunately there isn't. I couldn't find any actual solid research papers, so it's just an article. Kind of sucks. But it's between 40 and 60 C. My apologies. It's crossover temperature is what they call it. Under very rare circumstance, a plasma-like state can also form. So it's really interesting paper. I'll put it in the chat. Right there. Okay. So also there's a man, Googler, named Takaaki Matsumoto, or I guess you'd say Matsumoto Takaaki in Japanese, but he has an extensive body of work called electronuclear collapse, where you can actually create cavitation and what seems like muon formation or heavy electron bunching or grouping, and actually make cavitation without like ultrasonics. You're actually creating a phonon vibration through the electrons in the actual wire, especially with the nickel titanium. That was the hypothesis behind that, because as it heats and cools rapidly, it will create even more vibrations, and it collapses the hydrogen, or it collapses the boundary layer between the solid and the liquid, and creates a cavitation, and then whether there's extra heating effects and all that kind of stuff is something I've been exploring for a long time, trying to get to the bottom of. So hopefully that answers your question. And Googler, I'm getting ready to do another plasma experiment right now, so if all goes well, I just did another step up of power. Except, there we go. Voltage wasn't reading. Loose connection. Okay. So now, AM scope. AM scope software. I've been taking this thing out forever. And I'm gonna have to find the wire for this too. Let's see, I have any blank. I think I got some blanks. Add a little more alcohol to this. Before I start the experiment, I'll actually add some more dry ice to it too, so it'll be a reminder here. Okay, so now Slide blanks. 40 times I think is as high as I can go on this. Yeah. 60 volts. Slide covers. Pollen, onion, apple. Tons of prepared slides. I don't know if I have any blanks. That sucks. I can try to use 2 slide covers. Yeah, I don't know if I have any blanks, but I can try to use these slide covers. That's too bad. Then I gotta find a data wire that will fit this. Looks like a USB-C. That's right, there's a tiny little set screw in this. Yeah. Go. Don't know. Oh, it doesn't really. Link didn't show up. Try this again. Without. If I go like this, maybe. See if that shows up. For some reason, they didn't put the link down. Okay. Doesn't like me putting links in. Do it like this. See if this works. I'm trying to drop that link for you, but it's not letting me. It doesn't want me to put a link in. Nope, doesn't want me to put it in there that way. Yeah, I know, I even changed it to make it so it's not like an external link. Yeah. The electric sun. That's the idea. I'm gonna go fill up some hot water again to put on the top of this and see if it goes. I'll be right back. Yeah, it's not cold enough, that's why. I have to put some more dry ice in. Alright, well, it's under, it's science alert. It's called, the article's called Physics Just Discovered Second State of Liquid Water. It's published the 14th of November 2016. Here, you know what I can do? I'm gonna increase the power a little bit more. Let me go up to 100. About 190. We'll go up to 100. Looks like we're already getting some. Already getting some noise. So I'm gonna start that. Temperature 25C. Yes, Googler. Yeah, the thing in the back is a cloud chamber to see if there's any radiation from it, any additional radiation. So I'll be starting a plasma up here pretty soon. Okay. Let's see if I can do this. Do this real quick, show you. So if you go to harmonic hydrogen fusion, it's right here, and this is the website. Oh jeez, that scared the crap out of me. Well, the plasma built up. There goes another bit of glassware. So it must have ignited. Obviously. So this is the website up at the top. It scared the crap out of me. Man, I didn't think it would blow because like I had just a little. If I got a blowback, I had just a little bit. Well, I said if we were lucky, we would see the plasma. I don't know. We're gonna be lucky now. Just blew the top of my glassware off. Here. The sad part is I wasn't even recording it. I was trying to show this. Here, hold on a second. Here. Man, I had enough relief too. That's so weird that blew. It's so surprising. See that? This is dangerous stuff. I know, it sucks. I wish I had it on camera. I mean, you wouldn't be able to see it anyways, because it was down low. Well, let's assess the damage here. That sucks. That's so weird too, because it had plenty of pressure release too. For, like, this napkin should have just got blown out. That's all that should have happened. So that sucks. So I got plasma going, right, and then ignited the hydrogen, obviously. So that sucks. And then I'm not sure if I have another top. I might need to order one. I need to sweep. I need to sweep too. Well, that is a bummer. Man, that's so surprising that popped. It even blew out this piece too. I wonder where that went. Oh, it literally blew out the top of this too. That's crazy. I'm glad it didn't damage this. Didn't damage the cloud chamber, so that's good. But it blew out my plug too. That sucked, but was fun at the same time and exciting. I had a napkin. The napkin should have just easily blown out. So that's so weird. Yeah, no problem. I wish I had that on film, because it's my reaction primarily, me going, oh! But, damn. Well, it might be just microscope stuff tonight. Yeah, that sucks. Let's see, I do have this one other piece here, but it's for when I do I even sealed it and everything. It's for when I do the calorimetry. I don't want to take this out. I have to buy another piece. That's a bummer. All right. Well, that was funny. I'm just glad I didn't get blasted. Glad borosilicate doesn't like shatter into 1,000 pieces. Yeah, trying to cut tempered glass is a pain. You can use like a diamond file, put a little water on it, and try to break it like that. But yeah, it's challenging to do. Yeah, that doesn't usually happen. That's only happened one other time, a long time ago. And to solve that, I just made sure there's enough pressure. So like if it built up and it did blow, it would just blow out a little napkin. That's what I had set up. I don't know why it blew out the whole thing. Obviously, maybe it sucked it in there's some kind of pressure. So it sucked it in, the napkin in further. It sucks. Okay, well. That's too bad. Yeah, it built up too much hydrogen, and when I had it at about 100 volts, and when the plasma finally went off, it popped. So yeah, and I had a napkin in it, so if it did do that, because it's happened in the past, especially when you're right before you get plasma ignition, usually just this napkin just pops out, but for whatever reason didn't pop out. It just blew up the whole freaking thing. As long as it didn't break the flask. As long as I didn't break the flask, that's what's more important. Well, that was funny, man. I have not had that happen for a long time. Like, I've had it pop before, where it just popped this out. It wasn't a big deal. Whoops. Got distracted. Wasn't paying close enough attention. So I'll have to sweep and all that stuff. Man, I got this dry, so I really wanted to test it. Like and even the plug. This is the plug, right? There's nothing in it. This is the plug. It shot out the plug, and it must have hit the top of the rack and just shattered the top of the rack too. I feel like there's a delay on the stream quite a bit. Yeah. That was a short run. I think, oh, I bet it's because I just got too much crap going on with this. Right here. A bunch of ads on it. I don't need this. Okay. Putting that PTFE tape must have been a mistake. But man, I should have had plenty of pressure release. Okay, well. Let's see. I'm still gonna run this so I can do this. I'm just gonna change some things around. So huge delay. Yeah, it sucks. Hopefully it's better now. It looks like it's better now. Yeah, it was just because I had too much shit running. Boy, that fucking sucked. But the show must go on. So. This will be the new reactor. And this will be top plate. Last time I melted the other top piece. Second.
That was just silly.
Flask looks alright though, so that's good. Didn't want to have to buy another one of those.
Don't you do it.
Okay.
Stick this through here. Get it out of the way.
Ay, ay, ay.
Do you know of anyone who's worked on this using critical point of water?
No, I haven't, but I've thought of that idea. Higher pressures. But you're getting into a lot more dangerous territory when you start to do that. But I don't know of anyone in particular who's done that. That isn't openly available to the public. But it's a very interesting idea for creating a radical phase shift, right, at the critical point. Something I've thought about. So if you find something, please let me know. I haven't. I've actually looked. I've also looked for metallic hydrogen papers, and those are all shrouded in proprietary shit, and it's really hard to find that type of stuff. So if you find anything on like fluidity of hydrogen, or solid hydrogen, or super liquid hydrogen, anything like that, where it reaches a really low temperature, any type of research on that would be highly appreciated too. I've looked pretty deeply at that. Google Scholar doesn't pull up too much stuff. But yeah, that's something I've thought about quite a bit in advancing this research. I think there's something to be said about that. And if you look at like Pierre-Marie Robitaille's hydrogen, or a sun model, he's not the first, I think, to suggest this, but it makes a lot of sense to me, just from observation that we have. It's really, really interesting that there would be, a liquid, like a liquid plasma and plasma filaments. It would make more sense. Like, it wouldn't defy thermodynamics quite as much, like the laws of thermodynamics and electrodynamics in space, as opposed to Arthur Eddington's, like, 100-year-old nuclear furnace model. So, not saying that there isn't, like, obviously there's, we've detected helium and stuff like that from plasma, from fusion reactions, hot fusion reactions. And actually there's helium been detected from these types of experiments as well. So there's certainly something to be said about that, but yeah, a lot of stuff is unfortunately shrouded in intellectual property, and maybe, I don't know, maybe national security concerns, or who knows, but unfortunately we have kind of this, this paradox for, free energy and all that stuff. There's like a paradox there for how we conduct ourselves in socioeconomics with intellectual property and patents and all that kind of shit. So, but again, if you find something relating to the critical point of water using plasma, using a plasma, like a pressurized electrolytic plasma cell, that would be sweet. I would appreciate that. Or if you find any, and I've tried using OpenSci Hub too to look up a couple of these metallic hydrogen, because there's a lot of research that's done, like using high pressure with those diamond anvils, and creating small amounts of, you bring it to close to absolute zero and use I don't even know how many gigapascals they're using, but a lot, and turning hydrogen into a super fluid, like you can do with helium. I don't know if you've seen that's all pretty open, and years ago it got me thinking about that when I was researching it, like super helium, or super fluidity of helium, and how it works, and like, it's very, very interesting. If you can do similar things with hydrogen and it works opposite to helium becomes highly resistive, electrically resistive, I believe, in its superfluid state, whereas hydrogen becomes theoretically, hydrogen becomes like a superconductor, theoretically. So it's an interesting thing to think about. Okay, so that is plenty of pressure relief. Let's fire this back up. Yep, okay. I'm going to put some more dry ice into the cloud chamber. I'll have to clean this too a little bit. Got a little bit of broken glass in it as well. Just get it transferred all back. Yeah, I'm glad the cloud chamber didn't get busted. That would have sucked. Ooh. Hey, lady in red. Thanks for saying hi. Thanks for popping in. Enjoy the errand running. Where are you gonna run them to? That was cheesy as hell, huh? Alright, it's going to take a little bit to get colder. And I should probably go heat up the water on the top again. And actually, I'm going to put this underneath it this time. Oh, it's cold. Isolate it a little more. Still warm? Still warm enough. I'll be right back. Cold. Okay. Hopefully that'll start showing some tracks here soon. Let's turn this up a bit. What are we at? 23? There we go. All right. I'm gonna try to get a plasma going now. I'm gonna rush it a little bit. So we'll see. Here we go. $114 volts. Go, and I'll look at the cloud chamber and see. Getting vapor leak over here. Not seeing any tracks. Yep, just like yesterday. No. No real tracks to speak of. Getting a lot of steam in the chamber now, though. Steam in the reactor. Yep. About 70 watts of power, it looks like. Not getting any tracks at all, though, so that's not good, because At least we're getting tracks yesterday, right? No tracks means something's not right. Maybe it's not cold enough yet. Should just put the pans in with the dry ice first. Not seeing any tracks though. You can see some of the rippling on there. Stream. 130 volts. On the outer container. Well, I only have so much dry ice, so I'll do this. Gotta at least be seeing some tracks. Towel. turn it up a little bit. Okay. Wipe this down. Oh yeah, of course. Let's see. Might be done. Come on, light, stay. There we go. Go. Still relatively warm. All right. Try it again.
a leak.
Come on.
Cloud chambers are very finicky.
There's a track. Finally.
See some more. There's a track. Not coming from the direction of the reactor. I saw a few tracks. Oh, there's a track. I don't know if the stream's picking it up though.
I should probably take these gloves off too. Is it frozen?
There's a track. There's a track. There's a track. There's a track. There's tracks.
Okay. Try to get some video of this.
Oh, darn it. some tracks. Really small tracks. Man. Oh, I wish I wouldn't do that. Yeah, not seeing too many like prolific tracks though, so that's good. Good and bad. I mean, it's good because I'm not blasting myself with any crazy radiation. There we go. Just doing that. Should put some Vaseline or something around the bottom of it. Stop leaking air. Not seeing any tracks anymore again. Leak there. Oh, there's some tracks. Okay, there we go. Yeah. Looking good.
good. Yeah, the big vapor clouds are when it. Oh, it's freaking in the way. Uh-oh. Big vapor clouds are from it getting air leaks. Nothing on the cloud chamber. Really?
And very few hits on the cloud chamber.
What happened? Building up too much pressure. Wonder what type of connectors requires.
what happened? I see. Building up too much pressure. Thanks, Harbinger. Building up too much pressure. Alright, well, I'm going to pull it out just a touch. That might be too much. But we'll see. I'm sure it's going to be too much. There we go. Now back to trying to get this scope here. Don't know if I have old school. cloud chamber though. I'm not really seeing any cloud chamber action to begin with anyways. But it was fun. That was a fun experiment. I learned some shit.
I don't know if I can get this AM scope to work. Don't know if I have the wires for it. The wires are gonna find it. Go look upstairs. Yeah, there's electrolysis happening too on the hydrogen side. That's where the plasma's at, so the cathode, the negative cathode. It's making hydrogen, but then it's also immediately turning to plasma, right? It's kind of like it's just a spark discharge, basically. High current density. And the oxygen is in a whole nother tube behind it. It's a platinum electrode. It's just making the oxygen vent off. High surface area on that, but low surface area on the cathode, the negative cathode. It helps to create enough current density to make this plasma happen, like a point discharge. Kind of similar to like an LED, how the LED has this little whisker that goes into the active material. The challenge is to get material that can interface with the hydrogen dissociation and not break down. So nickel is a really good option. Tungsten and stainless steel both have a tendency to not only, well, stainless steel degrades. There's also issues with like chromium, other contaminants, but also you have a problem with hydrogen embrittlement, and it like breaks off, makes pointy bits. The nickel turns into a nice sphere. The best material is palladium, but it's very expensive. I only have a little bit that I'm saving for when I can actually get good temperature measurements. And I've yet to do plasma electrolysis with palladium. I'll be right back. I'm gonna go try to find this. See if I can get this scope like that. I will be right back. volt reading went down because I'm trying to mess with this AM skillet. What is the white traces of the white background? This is on the bottom left is power measurements. Those are just divisions. But yeah, I shut down the sample library. I'm trying to figure out the scope.
before presentation. Lots of different theories. What's interesting behavior?
that are in extreme environments, and we require novel power sources to be able to complete our missions, like a lunar and planetary surface power, exploring icy worlds with robots, even terrestrial power. We can transfer this to terrestrial applications. And then even we're looking at even ultra-high specific impulse propulsion. So LCF, we think, is the key to harnessing fusion within a compact system. It eliminates the highly enriched uranium, reduces safety, security, and supply concerns. It's compact, controllable, and maybe near zero radioactive waste. So how does it work? Well, traditional fusion heats plasma 10 times hotter than the sun, which is, hard to control. We address this with the pressure and temperature and containment challenges, where we heat a very few select atoms at a time. We can approach solar fuel density, and the lattice provides the containment. In the upper right, you'll see a nice depiction of what our lattice looks like. The green is your metal host, and the red is the deuterons. So the blow up there shows you that we also have this electron screening that happens. It's a cloud of electrons that makes the deuterons look like they're neutral to each other. And in our Bremsstrahlung irradiated experiments, we imparted kinetic energy to neutrons who can go anywhere in the lattice, and when they hit a deuteron and there's electron screening involved there, that induces the DD fusion. So we've identified the different parts of how this happens. I just talked about the electron screening that increases the fusion probability. You need a high fuel density, so you need a place to store and hold all this deuterium that you need for the fuel. And then you have a trigger. So all those three things are very, very important, and they create viable fusion. The graphic on the lower right there shows you a comparison of all the different fusion types of mechanisms with and without electron screening. The probability of fusion happening with lattice confinement fusion is quite considerably larger than traditional fusion, 10 to the 10 times to up to maybe even 10 to the 20th times. So what started it all? A researcher by the name of Gus Freilich in 1989 knew about Pons and Fleischmann and said, well, hey, why don't we, do a gas cycling? I've got this Johnson-Matthey hydrogen purifier. I can cycle deuterium through it, and let's just see what happens and look for neutrons, look for heat release. And he ended up not seeing very many neutrons above background, but he did observe temperature rise of about 17 degrees C in 15 seconds by unloading the deuterium, not with hydrogen and not with the loading. So that was interesting. So we did subsequent experiments to repeat the effect. And here's a schematic of the whole setup as far as, we had a supply gas, captured the gas afterwards, so we wanted to study what happened. So these are the results of the experiments. Again, heat rises in all of them at some point. So we also looked at these materials before and after the palladium-silver alloy, and it showed some really interesting spots, molten-looking spots and craters. And considering that palladium melts at over 1,500 degrees C and silver melts at over 900 degrees C, and yet the system was kept under 425 degrees C, something nuclear was probably happening. So with that, after that, a small group of researchers at NASA Glenn followed many different research activities with great interest. Bob Hendricks organized a workshop in 2011 at Cleveland, and we acquired a small amount of funding from our center director at the time. And the project was led by Dr. Steinitz and grew from a couple of researchers to about 25 or more over the years. It culminated in most recently published papers in PhysRevC in 2020. I'll talk a little bit about that later. And we held a virtual workshop in May of 2020 to announce those projects. And we transitioned it with a small level of funding for this year. And so we are publishing additional journal papers, and we have new experiments. So this chart's going to show you all the different triggers that we investigated. So we investigated, I told you about the hydrogen purifier, we looked at that. We also looked at slow co-deposition, electrolytic wet cells, and we saw some nuclear activity there. We also looked at low-level electron gun exposure under a scanning electron microscope and did activation of deuterated titanium. Then we kind of ramped up a little bit in trigger energy to X-rays, and again found some more activation and some nuclear signatures. And then we acquired a linear accelerator and did some brimstone irradiation, and we had lots of activation in those kinds of materials. We haven't quite done a lot of this yet, gas cycling and plated nickel alloys, but we're working with Ed Storms. He's doing a lot of work for us in this area, and then we're going to eventually do that ourselves. We also did a little bit with plasma trigger and found some interesting activity there as well. So we want to understand the variables and the key interactions to develop a heat source. That's the whole goal of these kinds of activities. So just a real brief overview of each segment that we looked at. We found that we could activate deuterated titanium. We looked at the beta signatures afterwards. We looked at CR39s, looked at all the different evidence of nuclear activity within this experiment. Same thing with the X-rays. It shows you our setup there, and we packed all this material into this swage lock thing. I remember doing those with Bob Hendricks. It was really hands-on work, I tell you. And so we found again a beta signature afterwards, which we think we identified later as we had some tritium there. So again, linear accelerator, we were looking at originally under the photodissociation of deuterium at 2.226 MeV or lower. At the time, I think what was the most challenging thing was really getting the evidence that there was nuclear reactions happening. Our later set of experience with linear accelerators, we were able to do neutron spectroscopy. At this time, we did gamma spectroscopy, which I did a lot of. I was really involved with that kind of thing. So we saw a lot of neutron activation of all of our materials. And we were able to scale things up with increased mass, beam energy, and so on and so forth. We also we kind of accidentally discovered a new way to possibly create medical isotopes for the industry. It was a relatively simple way to do that. CR39s again were employed, and there's an example of a triple track that would indicate DT fusion. So plasma reactor, we didn't do so many experiments there. We had to redirect ourselves to more of a linear accelerator part. But our test showed that we had excess power of about 4 watts with deuterated titanium, and then tests with palladium silver alloy showed even more at about 24 watts. We also saw some gas changes with gas that we gained a variety of.
You said CR39 is a good approach. I was hoping you could see something in the cloud chamber, some type of tracks in the cloud chamber, but to no avail. So it's a good approach for nuclear emulsion. A lot of people have used CR39 and then examine the tracks. that video. I'll look for that video. Nuclear fusion reactions and deuterated metals.
Added a couple of top-notch physicists to our team, and they developed our neutron spectroscopy system where we measure the neutrons. So you'll see in the graphs here just two of the dozens of materials and experiments that we did over the course of over a year. We actually went to an outside accelerator provider on Long Island. We would go 1 week at a time every month and do a series of experiments. So we were pleasantly, we were happy. We finally got the evidence that we knew we had. We just didn't have the equipment, the diagnostics to capture that. So you'll see that we have the peak, the main peak at 2.45 MeV for those neutrons. And you also see there's some higher neutrons that we didn't quite expect, know they were going to be there. So it's something that we would love to investigate further if we have time. And then that top graphic there is a YouTube video. You can get it on the website. We're going to have an exhibit here at the conference as well. So we'll have a handout.
Cheers.
So obviously, along with any kind of experiments you're developing, why are these things?
I'm gonna go to. Okay, well, she's gonna go into the theory here, so we'll go to that first.
What is facilitating the defusion chemical dissolve? And we contend that with our experiments, electron screening is an important player in this whole thing. And it reduces your Coulomb barrier to such a point where you are getting DV reaction rates at over 10 orders of magnitude compared to without any electron screening at all. The bottom line there you'll see is no electronic screening at all, and the x-axis is the center of mass energy. And the screening potential, depending on the host metal that you use, the screening potential goes from hundreds of EV all the way up to 3,500 graphic here. Excuse me. So we've shown that the electron screening can exponentially increase the fusion rates. And one of our PhysRef papers published in 2020 indicates that there is a higher probability of large angle scattering of screening So to wrap up, in summary, we've demonstrated multiple different nuclear reactions initiated by various experimental techniques. We have captured nuclear emissions in the form of neutrons, alphas, protons, betas,
Yeah, so that right there, you think that I would be able to see something in the cloud chamber if there's anything. So, it could be because I'm not using deuterated water, right? That could be a key factor. But the idea is the longer that you would run the cell, the more concentrated you make. That's how you make deuterium. Heavy water is just like prolonged electrolysis. But I'd have to keep adding water and stuff like that. Also, the idea of using the resonating tube is to increase the probability of bringing deuterium. I think deuterium is like 160 parts per million in 160
it's something like that. It's not very much. So it'd be interesting to see. That's why I was hoping to see some radiative tracks, but it also could be because it's in a borosilicate and it's underwater. It's going to be more challenging to see those tracks. And I haven't picked anything up on my radiation detector, which is a good thing, but it's also a bad thing, right? Because you want radiation in order to be able to capture it, to thermalize it, or do whatever you want with it to use it as useful energy. So. Oh.
Now, not all the methods that we employ produce the expected reaction products. It was kind of like a shotgun approach that we employed. Now, because we had read the literature about all the different methods that were out there, and we saw a lot of the same things that a lot of the other researchers did, including transmutation,
There's actually there's one that she didn't touch on, which is ultrasonic or bubble cavitation fusion reaction, just in deuterium. There's a lot of like trouble with some of the research that was done. There was a gentleman from, I want to say he's Russian, but he might just be Eastern European, that got into trouble, very fringe science, got in trouble for fudging some data. But it's another one of the methods that's used is using sonoluminescence, ultrasonic cavitation systems.
We found that the co-deposition experiments and the threshold radiation experiments, those were the more highly reproducible experiments in our investigations.
In the co-deposition, it's I think it's costing $250 just for just a little bit of deuterium hydroxide. Yeah, very expensive to do, although I would like to do that experiment because there's no plasma, so it's easy to measure the temperature. Just have to get some good RTDs. It's really good. It's just expensive.
Theory, the astrophysics and accelerator experiments have provided insights in addressing the nuclear barrier. And we have developed a critical concentration for expertise in multiple disciplines, experimental theoretical resources that we provide.
Yeah, you might be right, Josh. Yeah, I shouldn't give up on it. You're right. I mean, I was seeing tracks though, but it's just not. I wasn't seeing any tracks from the reaction site. But it would be for empirical purposes. It would be good to run a long period of experimentation and collect a lot of data, right? And then look at all the tracks and compile the information. There is another person who did nuclear emulsion. I don't think they use CR39. We'll figure it out. I'll look at this other video first. I'll go back and see what it was called again. It's already forgotten.
Following the evidence-based approach
In pursuit of a new energy source for deep space missions, NASA revealed a means of triggering lattice-confined nuclear fusion. Researchers placed deuterated metals in the gamma beam and measured neutron emissions from the resulting nuclear reactions. Nuclear reactions are initiated between deuterium nuclei, or more specifically, deuterons, that are confined in an electron-screened metal lattice as fuel. Nuclear reactions are triggered by gamma-ray irradiation of titanium and erbium metal lattices loaded with the hydrogen isotope deuterium. A deuteron is photodissociated into a proton and neutron. A neutron collides with a stationary deuteron, making an energetic deuteron. The energetic deuteron induces either screened lattice-confined fusion reactions or screened Oppenheimer-Phillips reactions. We will focus on DD fusion reactions in the metal lattice, deemed lattice confinement fusion, first. An energetic deuteron collides with a stationary deuteron in the lattice, and they fuse together. This fusion reaction results in either a neutron and a helium-3 atom, or a proton and a triton, producing useful energy. In the screened Oppenheimer-Phillips reaction, a proton is stripped from an energetic deuteron and is captured by an erbium atom, which is then converted to a different element, thulium. In the screened Oppenheimer-Phillips reaction, another action can happen. If the neutron instead is captured by erbium, a new isotope of erbium is formed and an energetic proton is ejected, heating the metal lattice. Each of these nuclear fusion reactions produce useful energy, such as for ion propulsion. Further development of the process is required to increase the efficiency of these lattice-confined nuclear reactions. Their applications range from terrestrial or long-duration space power, replacing solar panel arrays, to space propulsion, to the production of radioisotopes, thus paving the way for NASA to further enhance their space missions.
Good morning. I intend to do the impossible. I intend to explain to you folks here.
Yeah, I hope you're right, Josh. Hopefully it's easy. It'll be decentralized. Everyone can do it. Have their own heaters. That's my hope. Run their own Bitcoin miner.
How it works, and the other is based upon why it works. I'm going to talk about how it
Ed does like crack. He likes the crack. It's all about that crack.
That's how. I do not need to know anything about this or the mechanism. That's the why. We need to focus on the how. Why at this point is too far in the future to have any benefit. So I'm sorry, these theoreticians.
I don't know if you've already seen these. If you've already seen these, Josh. There's a lot of them.
So, let's get into the environment that hydrogen occupies. When I use the word hydrogen, I'm talking about all the isotopes of hydrogen. Very, anything else that might come along. So, hydrogen exists, first of all, in the labs, in the casing, palladium derived casing standard CD labs. This is a normal chemical structure. The structure is well known. There's very little ambiguity about it. It's been investigated for almost 100 years. A nuclear reaction simply cannot take place in that structure. And if some of you focus on that structure, you use that as your examples, I think, then you're wasting your time. It simply cannot happen under those conditions. It would violate.
Been doing it for a long time, man. 1989, 1990. He's been doing it ever since Paul
Another
Fleischmann.
environment must be created. I call that the nuclear active environment. That environment is outside of the crystal structure and is a place to which the hydrogen could go by a normal chemical process. So it goes from the
And he's a nuclear chemist. I mean, he's the best, one of the best people that can, best types of professions that can explain this type of thing, right? So.
last to the nuclear active environment by a loss of nuclear energy, like reactions. Once in this nuclear active environment, it now has the ability to form another structure, which I call the nuclear active structure. That structure is where the action occurs. That's where the actual nuclear reaction occurs. So each nuclear active environment might contain an arbitrary number of NAS. So we have the two variables, the number of nuclear active environment sites and then the number of NAS in those sites.
So one of the things that I kind of hypothesize that I'm trying to test, I'd like to test more, is that what he calls the nuclear active sites, essentially they're just ideal boundary layers of like quantum interaction, I guess you'd say, to to say it's such a dirty word. I almost don't want to say it, but for the 0 point energy, like plasma, like you were saying, same principle, creating different phase shifts for like the stripping away of the Coulomb barrier, like these boundary layer effects, where you kind of screen the electrons, however you want to look at it, screen these field energies to where they can cohere with each other in different ways. And I think that like it's possible to make. This is, of course, would take a lot of financing, but it's possible to make metamaterials that are far more efficient at doing this, and perhaps even in air environments. And just by applying a little bit of voltage across the substrate, kind of like a transistor, you can take hydrogen from the air, or oxygen from the air, or different elements from the air, so long as you knew how the interplay was, like the resonant frequency of those components, the elements. It's a pretty wild idea. It sounds crazy. It sounds crazy as fuck to some degree, but I can see how that could be possible. Like, you look at things like like the Schwinger limit, and even like looking at like an LED, how an LED and how efficient it is, it's really interesting to think about subatomic interfaces or atomic interfaces of different materials and how we can engineer things to in certain ways. If that makes sense. So I like his idea about the nuclear active sites and the like gaps, right? Having or cracks, however you want to look at it, because that would be where like a bubble would form. That is where you would have this kind of like a place for a vacuum where energy would need to fill in. Like nature doesn't particularly care for a vacuum. It's always trying to balance, right? So in those regions, you can have these extreme energy displacements. However you want to look at it. There's just some theories and hypotheses that I'd like to test with like this type of stuff.
So let's talk about the nature of the nuclear active environment. It has to be something that will attract the hydrogen. In other words, it has to look different than the lattice from which it came. But it has to.
Right. This band gap. It's a really interesting band gap when the atomic structures become very, very small. There's more of an interplay with the quantum energy fluctuations, the different electromagnetic fields that are present. It's interesting.
Not allow the formation of the hydrogen molecule. So it has to have what I call it, a range of size. It has to have a critical size. That's what makes it rare and difficult to form. That's why co-fusion is so difficult to reproduce. Getting that environment to form in its correct configuration. Now I believe that the gas, that the nuclear active environment are gas, physical gas, small cracks, but too small to even see with a so we're talking about something happening on the nano scale, which is also very frustrating because it's very difficult to study. I believe the gaps have a couple of nanometers in size, but once they're occupied, they become stable. And the reason for that is their occupation requires the loss of Gibbs energy. Now, for them to revert back to their original condition, that energy has to be in supply, but it's not available. So, fortunately, the condition in which cold fusion happens, once it forms, it's stable, and that's why we can continue to see the process for a significant length of time. The conditions for forming the nuclear active environment, I believe, there's a lot of conditions. The ones that I've focused on are the inclusion of inert particles.
Yeah, with the dark mode plasma or dark state plasma, that almost goes into plasma cosmology or the electric universe type of point of view, which kind of helps elaborate on the dark energy or dark matter of the universe, which is interesting. But in some, I don't know if you've ever done vacuum experiments, but if you run a DC vacuum like plasma reactor on the negative, if the conditions are right on the negative, you don't see depending on the certain voltage and stuff like that, but you won't see the actual plasma. But it's there because on the positive you see the plasma, and it depends on the arrangement, it depends on the frequency. It's always dependent on how you engineer it. But certainly it exists. It's interesting. There's a lot that's not visible to us in the universe. So that's interesting. And then there's also the idea of like hydrogen hypothesis that hydrogen is really prevalent in water. Obviously, they just discovered water is older than we think it is, like in the universe, but that there's hydrogen states, like I was talking about earlier, different liquid phase hydrogen or metallic hydrogen states that could very well be unknown to us, that are, in very cold regions, and perhaps, things like black holes are just super condensed hydrogen, and the reason why they look black to us is because of their absorption bands and things of that nature. So it's possible. I'm not saying that it's certain. Like, these are all theoretical. This is all theoretical shit. But that's the fun of science, is to kind of have these different ideas and theories and then test them. Right? That's the whole point, is to try to test them. So, it's unfortunate when you get a lot of pushback when you talk to experts in the field, like kind of just dismiss what you say. But that's the way it goes.
Particles of the material that melt above the molten point of flame. These, the gaps form between these particles, which are embedded in a random way in the material. And that formation is controllable by composition. But the size of the particle also plays a role. The reason why, frequently, when you have a supply of palladium, it will either be active, and if it is, all of that batch will be active. That's one of the characteristics of the field. And if it's not active, then nothing will happen. So the big issue is why is the material active throughout a batch? It has to be because there's a uniform structure created throughout the material. So, and that can be identified as the distribution of these particles. And these particles result during the fabrication of the material. Palladium typically is made chemically separated from its series. It results in a powder. That powder turns into a solid. Melting does that. Melt then allows large particles to float to the surface where they're removed, and small particles remain behind. So the question
We'll be right back. We'll make another break to take out the dogs.
Well, looking at this slide, look at the center, you see a cartoon of what how I would represent the embedded particle. The shape is arbitrary, these particles can have any shape, it doesn't matter what shape you use. You can see the gap that's formed around it, but somewhere in that gap, a NAS is formed, of the log of power against 1 over T. And C, A, B, and C, were the plots. Each of those are based upon separate samples done at separate times. But they were all done in a calorimeter, in using electrolytic approach, and so you'll go see what temperature range. And they're all solid samples. All have the same slope. Now, although each of these samples has a different magnitude of power, they all have the same slope. In other words, the slope is a characteristic of the LENR process in those samples, even though you get different amounts of power from each. That's important to understand. Now, if you look at B was a sample that was run when the current was applied. This allowed a composition of 0.85. See, the low point slide on a straight line. But then the current was turned off. This allowed the deuterium to leave the sample, and so the composition continuously reduced as measured periodically. Notice that all those points lie on the same line. In other words, the changing composition had no effect at all on the amount of power being produced, and yet produced the same slope. You look on the right, now that's a plot of temperature against power, and colored points, the red and the black, are run in an electrolytic cell. That same sample was taken out of the electrolytic cell and put into a gasoline cell. That is, simply exposed to deuterium without electrolysis. And then it was run in the calorimeter. Of course, you go to higher temperature, it's water. Notice that the data agree. The sample behaved the same way. In other words, electrolysis, there's nothing about electrolysis that makes that unique to forming LENR. Because the process will take place in various ways, having no relationship to the complexity that exists in the electrolytic process. That's also important to realize. Now, I could talk about the nature of the NAS. I'm just a little afraid that somebody will start throwing something at me because this is a very controversial aspect. If you want to talk to me privately, some witnesses, I'll be happy to talk about that. But let's talk about the nature of the nuclear reaction involving the different isotopes. The big problem is explaining trivium. I have a hard time doing it. So I made that my challenge. How can I explain trivium? Well, one way of explaining it is if you introduce an electron in the process. I believe the NAS consists of a collection of electrons and nuclei which are collaborating together, but in that process, an electron can easily be sucked into the neutron. So that makes sense to me. But what are the consequences? If you have two deuterons coming together, and I might point out too, these equations do not describe what's happening in reality. They just simply summarize what we had before and then what we saw later. This is just simply, they don't represent reality as to what is actually happening. It's not really what we're doing. So don't quarrel about the fact that those are two bodies, one body reaction. You can't conserve momentum under these conditions. That's an argument that we need to get into. Nevertheless, if you have two deuterons coming together with an electron, you get hydrogen 4. If you have hydrogen and a deuterium coming together with an electron, you get tritium. And if you have two protons coming together, you get deuterium. So we have a nice.
Yeah, that's possible. It's interesting that I'm getting hits electromagnetic spectrum just before, right? I'm not pushing it very hard. I'm trying to do like a long distance run. Like I don't want to push it up to higher voltages. I can get it to a wider plasma, right? It's gonna be hotter. I'm just see how long it'll run. If look at it now. Steaming away. Steaming away. Yeah, like I was saying, like you were saying actually, before the plasma kicks on, yeah, you hear that noise, you know, like the bubbling, right? The bubble popping stuff, and you know, from the electrolysis, the dissociation, but you see large spikes in the electromagnetic field around it. So yeah, you might be right about that. Like just another spectrum, dark plasma, or whatever it may be. Certainly something that could be a lot more tested for people who have the funds for it. I would love to have the funds for it. I don't even know how much money I've sunk in all these projects over this last like 8 years. Got to be up in the tens of thousands by now.
What would I call it? Pattern. I mean, nature likes consistent patterns, and here's a nice consistent pattern. Furthermore, we can explain the neutrons that come off when people see tritium. Neutrons are produced at a very low level, and they are correlated with the amount of tritium that's being produced, and that is shown in the graph on the right. The hot fusion produces at zero, when you plot the log of tritium over neutrons. But you can see there's a collection of data, all having values that seem to center around 10 to the 6th when you look at the log of neutron ratio. What causes those neutrons to be correlated with tritium? Well, if you apply my model to that would be tritium fusing with an electron and with a deuteron to form hydrogen 5, which would give off a neutron immediately. So the ratio that's produced there, which is as applied to values, would be sensitive to the tritium to deuterium ratio in a particular sample. So I can explain that. But then I hear somebody from the back yell, "You idiot! Hydrogen 4 can't form. It's known to form by giving off a neutron almost instantaneously." So all of this is nonsense. That's true. I admit to that. However, we're not working at high energy. We're working in a very low energy environment and under rather unusual conditions within the nuclear process. So I would submit that we have the opportunity to believe that it does not have to give off a neutron. But is there any evidence to support that? In 1992, Karabat was studying the production of photons within the gas discharge. He saw lots of them, did a very good job. But along with that study, he put some CR39 in, and he got the spectrum, ionized spectrum that is shown there. Now, there's several characteristics of that spectrum that you need to focus on. First of all, it all occurs at relatively low energies, below 6 MeV.
The dark plasma again, right? After the glow discharge is turned off in electrolysis, and then after emitted ions after the fact, right? Kind of interesting. I've been eyeballing some CR39, like everybody who seems to use it to verify what they're saying. Like, it's probably a good idea to use some of that, but I don't know if my microscope can handle it. I can't even get the freaking microscope to work. but yeah, it's interesting.
The intensity drops off in a nonlinear manner as you go to higher energies, and it consists of a number of separate energy peaks, all pretty much equally spaced. I mean, it's crude because it was CR39, but anyway, that's the basic picture you need to keep in your mind. Later, Brian Scanlon and I did a study under the identical conditions, gas discharge, and we saw the same spectrum, but because I was using a silicon barrier detector, I could determine its energy very precisely. And this is an example of the spectrum. Now, if we take from that spectrum and plot the log of the intensity against the energy, you get a straight line. In other words, you get this nonlinear decrease as you go to higher energies. Also, if you look on the right, if you plot the position in the spectrum against the energy, you get a straight line. This means that all of these peaks are equally spaced. Exactly what Proteus said. But I could do one thing more that he could not do. I could insert absorbers into this beam and note how much energy was reduced by this insertion. And by comparing that information to the mist cables, I could show very clearly that this is not helium. Everybody assumes that helium is being given off. Well, that's a problem. You can see. This is not helium. This is consistent, its behavior is consistent with an isotope of hydrogen. Now, which isotope of hydrogen, I don't know. But I'm encouraged to believe that it's hydrogen-4. Well, there are several implications of this idea, this model. In the past, when people assumed that helium is being made, we have a problem because helium does not diffuse very readily within a material. So, in order to get the helium out of the palladium deuteride, where it's measured in the gas, it has to be made very close to the surface, otherwise it cannot escape. And it always bothered me why this should be true. I mean, the true surface is different than the interior, but once you go in a few microns, it's identical to the rest of the sample. So why should the reaction be favored just in that region? It doesn't make any sense. If you accept the idea of hydrogen-4, you can see that problem goes away because the hydrogen-4 diffuses very readily through palladium. And so it could escape very easily before it decayed to helium. So that problem goes away. The second problem is, if you're making helium, why doesn't the helium fragment like it does when it's produced by hot fusion? That would resolve the problem of the energy states within the helium, which obviously the energy has to be dissipated somehow or another. hydrogen-4, that problem goes away. The helium is made as a consequence of beta emission. Hamud studied the production of radiation coming off of what looked like a cold fusion reaction, and he found that the radiation had a half-life, it had a decay, and he could measure that decay. I suggest that what he was actually measuring was the decay of hydrogen-4. Now, there's several other implications. One is, if you use pure deuterium, you will not make tritium. And that's very good to know, especially in a large-scale generator. You don't want to make tritium. So you want to use pure deuterium.
So he's suggesting hydrogen-4, which is a very bold statement. Kind of interesting. Yeah, I don't know. Using light water, I don't know if I'd be near that, what I'm doing. And to be able to test that is challenging. But that's interesting.
Period. If you use pure hydrogen, on the other hand,
There's so many fucking theories in this. It's just like mind-boggling how many different people have takes on this. I'd rather just, if it's useful, than like freaking put it to work, right? It's one of those, it seems useful, we should be putting it to work. Theory doesn't matter that much. The more that we apply it, apply the science of it, probably the more understanding we'll get of it, right? So, yeah.
and which many people are studying.
What do you think, Josh? What's your theory? What's your best theory?
Which does make excess energy. You will make tritium. And the reason is that the hydrogen makes deuterium, and then that deuterium finds a proton, which makes tritium, based upon my mechanism. So you should see the slow growth of tritium in the cells that are based upon like hydrogen. Now this would be a real disaster in a power plant that's making megawatts of power, because the amount of tritium would grow to actually dangerous levels under those conditions. And so that's another variable that needs to be considered when you apply this. Well, for success, we need three things. We need to make more of the nuclear reactor environment, and I've described how that can be done. And there's lots of different variations of that. Some work better than others. I happen to like mine because it seems to work quite nicely. We need to stimulate the formation of the NAS. I believe you can do that. In fact, Robert Goddard, I believe, is doing that by applying his pulse current. That's the variable that his pulse current is affecting. And then the use of higher temperatures. Now, higher temperatures that are important. Most of my samples at 20 degrees centigrade, where most people work, look dead. It's only when I heat them that I start seeing it. And of course, as we saw earlier, the temperature has a very characteristic effect. I would suggest that many of the failures that people have reported would have been successes if they had simply worked at a higher temperature. Okay, thank you for your attention. I'm willing to duck anything you throw.
It's Ruby. Did I miss you saying that you were going to tell us how you made this material?
Yes.
Did you say that?
Well, yes, you incorporate particles of the correct size into palladium. Now, I do that because I'm self-funded. I do that in the most simple way possible. I take a piece of palladium, I'll roll it out, paint on the surface using acetone as a slurry, suitable particles. Roll this up so that now this surface is incorporated into the structure. Melt it with a flame, get a little button, roll that out into a convenient shape and size.
That's the key, isn't it? To say, I don't know. I appreciate that, man. Because I don't know either, right? That's about exploring, trying to figure out, testing your intuitions and testing your hypothesis. Yeah. It's interesting. The plasma states of energy. I say matter, but I mean, everything's energy, right? So the plasma states are very, very fascinating. Especially like you were saying, the invisible ones, the things that we can't see. I guess we're trying to see them. We're trying to figure it out. So I appreciate your honesty.
Heated in the furnace and air to oxidize the surface to make it active. For deuterium gas, load it up, reacts very rapidly with deuterium, and then put it in calorimeter, and it makes heat instantly. Now the only challenge, of course, is getting the right size particle. If you use the wrong size particle, nothing will happen. And right now I'm exploring with more precision the right size particle.
I think he said in the past that the particle sizes doesn't go over 10 nanometers. But I think he says like 2 nanometers is ideal. Something around that, 1 or 2 nanometers, very, very small scale. So that's one of the reasons why I incorporated the nanoparticulate graphite into this electrolytic cells that I use. That's why it's like dark like it looks. Is to create those little gap sites with a material that won't get destroyed by the heat. And so, of course, there's like a probability of them coming across the boundary layer of the plasma at the surface, but you gotta make do with what you got. I mean, I would love some chemical vapor deposition chamber, and I love all these wonderful tools, but they're very, very expensive, so you gotta make do with what you got and try to make it work. And then, if you're resourceful with those things, they can be of use to other people out there. So if you're interested in how I made that, if anybody's interested in how I made that, there's several methods, but the easiest is Robert Murray Smith has a method where he takes graph oil and exfoliates it using sulfuric acid, lower voltages, basically unzips it. Then you have to put it through an ultrasonification bath for like 8 hours minimum, and then clean it up really good, and you'll get nanoparticulate graphite. Now, I'm not saying there's probably some graphene in it, but I'm not saying it's graphene. And then recently, Tech Ingredients, I think it was just today, I just watched the video, just made graphene using what Rice Institute did. He made a really good video on that. So that's something that I'm looking into. Like to do. I already have the quartz tube for it, but there's a problem with it becoming. I think there's a problem with it becoming hydrophobic. But I'm not sure. So, something to experiment with. It's very interesting. But he does make small amounts of graphene according to the paper. And there's also an Indian gentleman who describes how to make it. He links those 2 papers in his videos. So if you haven't seen that, Tech Ingredients, he has a really good
anyway, that's the way you do it. Now, if you're going to apply this industrially, I think the use of a material, even this material, is a waste of time. Materials are too difficult to create in a reproducible way. You have to do it, make the material by nanomachining. And I would suggest that if there's cracks, gaps, you identify the gap width, and then machine those by nanomachining techniques, which are available now, into nickel, for example, and make the concentration sufficient that it produces a large amount of power, but not enough to melt the sample. And then you can turn this out in tons of amount in a totally reproducible way. I think that's the only way this is going to be being practical. And I would suggest that the sooner you get to work looking at it from that point of view, the rods have something that works.
Another question. Basically, you just answered it, but I mean, why not use a focused ion beam milling machine, which is commercially available from FEI, for example, and other places, for drilling or boring holes in semiconductors as a standard tool, and drill or bore a bunch of nano-sized holes on the surface of, say, palladium, finally, control smooth, polished palladium, and then see if your theory is correct. Put some deuterium in the holes, make them various depths, various diameters, various angles if you like. You can cover them up again and make them void if you want, and see if in fact you know exactly where the holes are because you drilled them there. Does it work? Do you go back and see evidence of reactions after you've waited a certain period or done whatever it is, whatever magic sauce you need to make, the reactions happen, and study it that way? And those are existing tools. Or, give you the address of FEI, and they'd probably volunteer to be partners, maybe. I don't know. I mean, maybe they could be talking to them.
Well, I didn't detect a question there, but let me expand on that. It doesn't matter. I don't think the shape of the crack or the material, the gap, is important. I mean,
That was a really solid suggestion, though. Even though it wasn't a question, I think he has a way that you can test it and reproduce it. And you can look at it under SEM or Raman spectroscopy, diffraction. I mean, there's ways to look at it. So I think that was a really excellent suggestion that this guy made. I'm stopping the video and talking over it a little bit because I want it to be a reaction video, right? Make it more of a reaction video. I know this is like a live stream, but that way I don't get me in any trouble. Although I am acquainted with some of the people at the ICCF, but it's probably good to do it that way.
from the point of view of the atom, all shapes are the same. So, but you do have it to make it the right size. So with nanomachining, you have total control. I mean, it's relatively easy to nanomachine a gap at 10 nanometers. That's too big, and there's obvious ways of making it smaller. The challenge would be to apply those slowly until you reach the critical size, and all of a sudden you turn on, and then you know that's the size that you need to make it on a regular basis.
Wait a minute here.
Turn on. Apply those obvious ways of making it smaller. Get the right size. So with nanomachining, you have total control. I mean, it's relatively easy to nanomachine a gap at 10 nanometers. That's too big, and there's obvious ways of making it smaller. The challenge would be to apply those slowly until you reach the critical size, and all of a sudden you turn on, and then you know that's the size that you need to make on a regular basis. But any technique that would produce the right size hole would work.
In the semiconductor, you see it's all, the FEI machine is programmable. You can make it do anything you want, any size you want. Down to some atomic limit. I don't know what exact limit is. It depends on the material. But calling FEI, just getting them on board, just take a phone call. Or on board. It just seems like an obvious
1 nanometer is 10 angstroms. How many Planck lengths for 1 nanometer? I know, I think that has to do with time. Or I mean, light movement. But let's see. So the question might be how fast does light move across 1 nanometer? Holy shit. 1.61605 to the negative 26th nanometer. Very, very small. Double check that. Oh no, this is saying it's 1.6. Oh yeah, to the negative 26. Gotta read the whole thing. 1.61604999999 to the negative 26 nanometers. Incredibly smaller than 1 nanometer. Just a curious question I had.
It's a standard technology. It's sitting there waiting to be used. It's been there for years. It's not new. I could probably...
You guys, plonk. You guys should say plonk. That's the more appropriate way to say it. Plonk.
Find some people that might be interested in doing that right here today, if we were to call on the phone.
Yes, and I'm talking to people that do have that. The problem is it costs money.
Yeah, the world's a stage.
Yeah.
You're going to want to help.
Anyway, let's talk about that during the intermission, and I'd love to explore your ideas. We have time.
Yeah, I get it, man. Nice pun. I hope not. I hope nobody has any problems with that. I don't think anyone will. But I like listening to, especially people in this field, I like listening to all different sides of things. And him saying, because he originally discovered this from his own experiments when Hans and Fleischmann happened. He used the material that was that had deformations in the palladium, right? That's where he discovered this, and he kept going down that road, and it kept yielding good results, which was different than a lot of other people did. So, I don't know if anybody has it all figured out, but it's good to listen to. I think it's good to listen to different hypotheses from different people, and he's had positive results, so it's good to listen to, right? Yeah, the Planck scale is way fucking down there, right? Imagine making a material. So the atom obviously is way larger than the Planck scale. And I don't know about the quantum chromodynamics. I don't know about that whole thing. Sometimes I think that we are fooling ourselves with smashing shit together, like electrodynamic cavemen. But yeah, it was just something I was thinking about. We'll move on to someone else. This is almost over, so.
Well, I think 1 nanometer is too small and 10 nanometers is too large. So I think 2 nanometers is just a talking point. We obviously would have to explore that in much more detail to know what exactly to focus on. But the big issue is that we need to focus on the size of gap. And that hasn't been considered in the past. Well, let's talk about this because there's a huge amount that I have not said that needs to be said if we're really serious about going down that
All right, this one is really interesting.
Statistic representation of. Hi again, everyone. So yeah, I'm Eric Ziem. I'm a postdoc under Dr. George H. Miley in the Nuclear, Plasma, and Radiological Engineering Department at UIUC. So I'm going to be presenting a little bit from my PhD, which I covered LENR. And some.
We tried, the LENR forum tried to chat with this gentleman. He agreed to it at first, but then, for some reason, he went back on it. So, saying that George Miley wouldn't allow him to do it for proprietary reasons. So, it fell under intellectual property. Once again, socioeconomic thing, the energy freedom paradox, whatever the hell you want to call it. Walled garden of knowledge reared its ugly head, so that's unfortunate, but he has a wonderful presentation and has done some really great work. So I'll try reaching out to him personally, just to see if he'll share the algorithm he uses. It's pretty cool.
Some of these results focused on alpha particle detection using CR39 during a deuterium DC glow discharge with palladium electrodes. So first things first, what's LENR? I really wanted to just define what that is, and to do that I'll use two example experiments. The first is done by Cecil in 1990, where they implanted high-energy deuterons into a 1 micron palladium film. And at these high energies, you get your typical DD fusion reaction byproducts, which they monitored using a silicon surface barrier detector. So then they turn it off and then apply a electric current. So there's nothing's incident on these foils. So your interaction energy is more or less room temperature. You'd expect 0 fusion events. But they measured 3 MeV and 5 MeV particles. Very atypical, not even the traditional DD fusion results. The second is chambers. They used low energy ions of deuterons incident on a titanium foil, also using an SSBD, and they also measured 5 MeV particles. I particularly like this one quote of, "The reaction we have observed can only be due to a novel, previously unobserved nuclear process involving deuterium." So we have low interacting ion energies plus unconventional nuclear products. That leads to the name low energy nuclear reactions. The low energy is solely on the interacting ion energies, not the byproducts, which is a common misunderstanding. So I focus on plasma material interaction, that is deuterium discharge interacting with palladium cathodes. On the right is a little figure just depicting how do deuterons impact the surface and lead to defects, and those defects then trap the deuterons. And I did.
See, once again, he's talking about defects as well, right? Just like storms. It's interesting. So yeah, it got brought up again.
Thermal desorption spectroscopy to show, oh, these bound.
He's labeling them as void clusters. Interesting.
Deuterons don't exit the lattice until about 450 degrees Celsius. So we know that there's bound deuterium inside of this lattice. And the hypothesis is these clusters are necessary for LENR. So then with my methodology, reviewing the field, I saw a lot of reproducibility problems, not just in the prior 2 experiments, but all across the field. And that's mainly, well, the mechanism is still unknown. So I wanted to keep it simple. And to, like when you're investigating something that shouldn't really exist in nature, you want to keep it as simple as possible. So to do that, I use CR39 and a DC discharge. On the right is the discharge diagram, where the detector is just that piece of CR39, and I'll explain how CR39 operates. So, using this methodology, I wanted to focus on making direct observations as precisely as possible. And then from those observations, make abstractions and see if you can make inferences from those and see if they will be consistently corresponding between them. And then hopefully you can get some avenue for future work. I didn't focus on any type of partial theory or modeling or predicted phenomenon. This work was more or less a stepping stone to kind of use as a robust check for future theories. So why not an SSBD like these other groups? Why CR39? And the entire reason is mostly no external electronics, sensitive to noise. I am using a DC discharge, and it does often go into noisy regimes, and that will influence your electronics. So CR39, it's just a polymer. When an energetic charged particle is incident on the surface, it travels through it, penetrates it, it causes ionization. The ionization will lead to polymer chain breaking, and then you can etch the surface. That damaged volume is preferentially removed compared to the bulk. That leads to tracks. And then you directly observe those tracks. This is an example of 3.5 MeV alphas with an optical microscope.
Yeah, you've seen this one, I'm sure, right? This is a really good one. Oh yeah, very cool. But yeah, there's I was just actually looking at that. I 3D printed stuff, but there is with Octoprint, they have machine learning that detects if your print's getting fucked up, so you can just automatically cancel it. It's really cool. Very, very cool. I'd like to set up a camera on my 3D printer to be able to do that. Cool stuff. We're living in an incredible time, that's for sure. I am gonna go and see if I can find some Vaseline. Not for what you think. Or maybe it's for what you think. But it's for the cloud chain. And I'm gonna put it on the bottom of it, and I'm gonna see if I can get this cloud chain ready to go again. Since this plasma's running for a long time, gonna be running for a long time, I might as well try to get the cloud chain ready again. Like you said, Josh. So I'm gonna go see if we have some Vaseline somewhere. Hardly ever use it anymore. Because I'm married and everything. I'll be right back. Body lotion works way better.
So if a nuclear reaction produces energetic charged particles, that will damage the CR39 and lead to tracks. So, my objective, determine experimental conditions that repeatably produce LENR. Great. So, deuterium discharge plus CR39 detector, it's about 5 centimeters away. Shocking, tracks appear. Okay, so you've got some tracks. You have to quantify the size of these tracks. You can even do 3D depth profiling to get a little bit more information. But you need to calibrate how does this detector respond to known ion sources. And I'll cover that. But we conclude that these tracks were consistently corresponded to roughly 100 keV alpha particles, helium, emitted from the palladium electrode. So we currently don't know any mechanism that would accelerate ions to these energies, hence we conclude some sort of nuclear process occurred. So the procedure, I'll just go through this quick. You have your CR39, you do a deleting etch to remove the first 100 or 200 microns of material to make sure you get rid of your background. You do your radiation test, or you do your experiment. You do a track etch. My parameters were shown there. And then I designed, built, programmed an imaging apparatus to image these entire surfaces. Like these are 2.5 by 2.5 centimeters, and that's a lot of area to image at a micron resolution. So I wanted to automate that. And this is an example of my autofocus. It's just looking for, let's optimize the sharpness, take an image, go to the next position. And then you can stitch those together to get a nice big image of your total surface. So then with that image, these things are like gigabytes in size. I didn't want to just sit there and looking at the image waste my time, so I used this freeware Elastic. It's a supervised machine learning for image classification. So it removes the human out of it once you train the software. So this is just a raw image. You say this is my green is background.
I think I just heard him say it's freeware. That wasn't what he was holding. That wasn't what was proprietary. It's just their whole process of doing LENR. That was the proprietary bit. I'm pretty sure you just said that the machine learning tool is Elastic is freeware, so that's cool. I couldn't find any Vaseline, but I might have some in some of my chemicals. I'll take a look.
Ground, red is foreground. Then you can threshold these local pixels into objects, and then you classify those objects based off of their shape, color, relationship to one another, and then you can export the tracks. And then I get what I call a track density heat map to see where are tracks occurring on my chip. So now we're at what caused the tracks. It could be protons, alphas, or some other ion. It could even, I hypothesized, well, maybe it's plasma radicals or surface charge effects. I wasn't sure, so we just have this observation of small, shallow tracks in Sierra 39. On the right, the far right, are examples of tracks from other ions. So we have to rely on the calibration of the Sierra 39 to really extract what is causing these tracks. So with the calibrations, I used americium and an air gap, just measuring the distance between my detector and my alpha emitter up here, and then you calculate using the transport of ions and matter to see how much energy is lost as these ions penetrate through air. An example of just 5.5 MeV alphas is on the right, and the very first calibration is measuring that minor axis for the track versus its energy. So when you attenuate the incident energies, then you measure the resulting tracks. So that's one. Then another is let's etch these things multiple times. See how they, how each energy interval progresses with 1 hour etch, 2 hour etch, 3 hour etch. And you can do the minor axis versus incident energy for each etch interval, and then kind of as a corollary, measuring the slope. How much does the minor axis change with etching time? And then another one is track depth. And I wanted to do this because particles can produce the same track diameter, but they would have different depths based off of their stopping power. So that would be able to discriminate between, say, an alpha or a proton. So I'm mainly, again, looking for consistency. If tracks are due to protons or other ions, then a discrepancy will be seen between the metrics. Here's an example of my 1 hour etch calibration with example images of tracks. The tracks from the plasma experiments are about 8.5 microns. So I focus on the lowest 5 energy intervals, and that goes to 120 keV incident energy estimates. So now going to just track counting, how many tracks are occurring for each experiment. This is a graph for just track density versus fluence, which is how many ions are interacting with my electrode. It doesn't take into like secondary electron emission or backscatter. But the black is the deuterium, and then red and blue are my controls with hydrogen and helium. And deuterium was typically about 100 times higher in track density than the controls. This is an example of a hydrogen track, and then this is, as the fluence increases, it saturates the detector. So moving forward, this is now an example of, here are my tracks. Let's throw it through the gamut of all these measurements. So here's the histogram for all my tracks. They're minor axis. They appear monoenergetic. Let's look at the calibration curve. That leads to 120 keV. Then let's do the progressive etching. After each etch, you measure, you export, and then you compare it to the calibrations. These are calibration curves for my americium source tracks for each etch interval. And for each one, it always corresponded to roughly 120 keV. I also measure the slope of the minor axis versus etching time, so it's a little different, but it also leads to the same conclusion, roughly 100 keV. Now, depth profiling. I manually measured 200 tracks. That was a lot of fun. And I also did that for all of my calibration tracks from americium, do the fittings, all that fun stuff, 93 keV. So what else can be extracted from the 3D measurements? As I was doing that fun depth profiling, I'm like, well, these things are conical in nature. On the right is a depth profile with a bunch of fittings, and you can bifurcate the walls, so divide it in half, and that can even give you an estimate of...
I didn't find Vaseline, but I do have some silicone to use that.
Where is this particle coming from that hits your track? So I scanned 2 samples across 3 y-axis positions. That's a lot of measurements. And then I back calculate trajectories. On the right is just a little graph of all of these trajectories, and it's, oh, interesting. They seem to converge. This is a cross-section, so a 2D projection of that 3D data at the z=5. That's where my electrodes are located. And oh, they're all pointing towards a similar point of origin. So that is evidence that, okay, these things are coming from my electrodes. So that removes the possibility of, say, cosmic rays or some sort of galactic event or atmospheric radon, just like depositing on my CR39. So in summary, I'll go over, we've got shallow tracks. We've got our minor axis versus incident energy calibration curves relying on americium. That leads to 120 keV alphas. We've got the track etch progression. That leads to roughly 120 keV incident alphas. The slope, roughly 100. The 3D profiling for the depth, that was roughly 100. But I also used that same measurement to kind of check my optical automated analysis. So now, like, I was measuring these manually, the diameter, and that was roughly 100 also. Then there were other experiments just replicating z=5. That's the distance between my detector and the electrodes. Do the same stuff, roughly 100 keV. Now, I then use TRIM, the transport of ions in matter, that takes into account how much energy is being lost as these ions traverse a pressurized vessel. That would be 5 centimeters in 10 torr of deuterium. So you back calculate that, that leads to, oh, they were emitted from the electrode at around 138 keV from the cathode. Now, I didn't show any of this. Now this is stuff that's just supplemental that was from my PhD. Let's move the detector back to z=10. Do the same thing, lower incident energy, but you do trim through 10 torr of, at 10 centimeters, shockingly 138 keV, right on the dot. And then from this data, you can also do solid angle dependence to estimate emission rates. How many tracks are being produced per unit area per unit time? And those also corresponded well together. Now, this one is a whole bunch of other stuff, but the main thing is this, the question, what else might be causing these tracks? Plasma radicals, or maybe some sort of surface charge effect is accumulating that's leading to these tracks? And to kind of address that issue, well, I just sputtered a whole bunch of gold. Well, first one was 100 nanometers, and shockingly, there were tracks. There were a significant amount of tracks, so that kind of removes the plasma radical hypothesis. But simultaneously, I had unshielded detector in there, and that one had larger tracks, roughly incident energy of 122, whereas with the one with gold, they were attenuated, so roughly down to 100 as they lost that energy as they went through the gold. You can do trim again to say, okay, now take this input into trim, has to travel through 100 nanometers. What's the resulting energy? Roughly 90. Okay, 90 compared to 100, that's in fairly good agreement. And it also gives you information on ions with similar stopping powers in CR39 can produce tracks that look almost identical. Two possibilities were palladium ions somehow getting accelerated up to 5.5 keV. Just saying, okay, sure, they might be getting up to that energy, but they have a very low penetration distance in that gold. So that removes palladium, and the helium-3 is still potentially a cause. I have not been able to discriminate that. As for the 500 nanometer of gold, reduced back down to more or less near the controls of track densities. So that removes the possibility of these being, say, protons. They'd be able to traverse that 500 nanometer thickness of gold and then cause tracks. And then just the normalized track density for my controls were consistently 100 times lower than what I was doing with deuterium. So that also gives supporting evidence that plasma radicals and surface charge accumulation did not cause these tracks. And then last with 3D profiling for the track trajectories. I designed, built, programmed this imaging apparatus and analysis pipeline for automated track detection, and I calibrated my CR39 with americium-241, and then I did extensive experiments to establish charged particle emission that was consistently corresponding to roughly 100 keV alphas, which is noticeably different from the 5 MeV particle group from Cecil and Chambers. So what's going on? Well, pretty simple explanation. They used shielding to block their SSBDs from any kind of stray plasma radicals. And that shielding was typically, say, 10 microns of material. That's going to block all of your low energy alphas. So that's pretty quick. And it was repeatable. I don't have the slide up here, but I did the same test with deuterium, get the tracks, evacuate the chamber, bake it out, make sure I release all deuterium from my electrode, and then do it with hydrogen, no tracks. Then do the same preparation procedure, do it again with deuterium, back to tracks. So that 100...
All right, what did I do? Yeah, it was a good experiment. Well, I just got this set up. Then I nuked something. I don't know what I nuked. Might have shut it off in time. Just arc something. Sure, I just bumped some shit together.
carbon is on the ground, on the bottom. Oops. Trying to set this up. All right. I have several fuse redundancies, so something went off. See that? All right. Well, let's turn it back on and see. Nothing there. But we can see the current spike. Let's look at it. Let's see what we did. Not that big of a current spike. Oh, I see. I totally know what we did. We shorted in there, in the cell. Yep. Because I can see a carbon pathway. Oh, I fused the electrodes together too. Whoops. Because I bumped it. Oh yeah. Freaking tack welded it. Tack welded the freaking positive and negative together by bumping it. Well, I don't want to rush into anymore. I rushed into the experiment a little bit because I wanted to get the plasma going, and then I bumped it. So that might have been it. That might be life telling me to be done. Don't want to push it too much, but I'll show you what I did. Yeah, one sec. My apologies. I tack welded the two electrodes together. Here, let me get this bigger. See that? The two wires? Because this got twisted. I bumped it and it twisted, and then tack welded those two together. So, done. Done for the night. But you could take a look at this. This is pretty interesting. So the ball is gone. The ceramic has been cooked away. So is the silicate. The quartz, I should say, the quartz tube. There's more degradation. So I'm not sure how I'm gonna get over that. That sucks. Challenging things. I also noticed that the steam was coming out. There's a lot of carbon deposits. There's this gray graphite. Yeah, it was fun. That's usually the way it goes, man. It's always things happen, right? Setting up for the cloud chamber again, and then yeah, I just don't want to rush into it, and I want to take my time and set it up better, because I rushed into that since I blew the distillation Y piece, you know, since I broke my glassware. So I rushed into that, trying to get the plasma going. It's not always good to do. But maybe we can see some tracks. Yeah. So I can do that briefly. Let's see. So
Okay, let's try something. Are you able to see any of those? Damn it. 1 second. Just setting up something. Okay. Put a sample of the material that was in the cell, a little bit of the carbon and nickel. We'll see if it has any radiative effects. It'll take a second for the cloud chamber to get going though.
So far, not seeing anything. That's weird. Why is there like a big wall right there? That's odd. Or just the way that the alcohol's falling, maybe. There's a track. Oh. Seen plenty of tracks now, but nothing around the magnet with the nickel carbon. Also getting a lot of red detector hits. Hopefully you guys can see those. I'm not sure. Probably not so well. Yeah, it's kind of close. Yeah, I'm not even sure if that can be seen on this webcam. All right. Well. That was cool. Josh, Emergence channel, huh? I will look into that. Looks cool. Have you watched anything about Casimir? I know about the Casimir effect quite a bit. I've watched a few things about it. Yeah, but I haven't seen that video. I will look into it. Good. I'm glad you could see a few particles. I can see them. It's just hard to catch them on camera. So I'm gonna try to get them on my
my phone. But that concludes the experiments for tonight. I had some epic failures, that's for sure. So thanks for watching, guys. I appreciate it. Nothing off the material though. So no tracks off the material. So yeah, compression, and also just the camera as well. Anyways, guys, I'm gonna get some video shots of this with my phone, hopefully, and post that, and call it a night.